We'll start with some overview here, and we will start with functions whose domain is all real numbers. The domain of the following functions is the set of all real numbers: polynomials, exponential, and if you have any odd root. Fx, which is sine of x, and also cosine x. Also the arctangent x and the arccotangent x. But there are many other domains which are more complicated. For example, the domain of the rational function Rx, which is a polynomial over polynomial, is the set of all real numbers such that the polynomial at the bottom Qx is not zero. The domain of the logarithmic function log base a of x or ln of x is x greater than 0, only strictly positive. The domain of the even root functions is x is greater or equal to 0. If you have a logarithmic function, then x is strictly positive. But if you have an even root, then it's positive but also can include a 0, so it's x greater or equals to 0. Domains of combination of functions. The domain of f plus g, f minus g, f times g are the intersection of the domains of f and g. The domain of f over g is more complicated. First of all, is as above, is the intersection of the domains of f and g, with the additional condition that g of x cannot be 0. The domain of the composite function f composed with g or f of g of x is the set of all numbers in the domain of g such that g of x is in the domain of f. Most of the complications that we are going to see are when we are combining more than one function together. Let's do an example. Here is f and g. Find the domain of the following functions. First of all, k of x, which is f plus g, and then h of x, which is f times g. The domains of k and h are the same because they are the intersection of the domains of f and g. This is an even root, so we know that x has to be greater or equals to -1 because x plus 1 has to be greater or equals to 0. And from here, this is pretty easy, we get that x cannot be 0. Let's combine that. It's easier to combine on the real line. The first domain is including everything that is greater or equals to -1. The second domain including everything on the real line except that cannot be 0. When we look at the intersection, we get this. So we get everything that is greater or equals to -1 but cannot be 0. It means that the domains of both of those functions is when x is greater or equals to -1 and less than 0, and when x is more than 0. Example. Let fx be x to the power of 2 minus ln of x, and gx be ln of x plus 2x. Find the domain of L of x, which is f plus g. The domains of f and g are the same. X has to be strictly greater than 0. The domain of L is the intersection of the two domains. because they have the same domains, then the intersection is the same, which means x is greater than 0. What happens if you actually calculate L of x? Then you get x to the power of 2 minus ln of x plus ln of x plus 2x, which is x to the power of 2, as you can see, plus 2x. This is a polynomial. The domain of L is x greater than 0 in spite of the fact that it looks like a polynomial. It's almost like the be careful that we had before. By simplifying L of x and getting the polynomial x to the power of 2 plus 2x, we are rewriting the function differently, but we really get a different function because the domain is different from the original domain of the function f plus g. The domain of the composite function f of g of x is the set of all numbers in the domain of g such that gx in the domain of f. This is a little too difficult. Let's see the details. In step 1, we really care about the domain of g. But in step 2, we have to find all the x's in the domain of g such that gx is also in the domain of f. We can think about it as moving through the following chart without interruption, or if you want, moving in the pipes. We have to start with x, and because we first apply gx, x has to be in the domain of g of x. But then we are in gx, and this is now the domain of the function f, because we now apply f. So first we have to find all the x's that are in the domain of g. But also, it's not enough. We also have the g of x will move in the pipe, which means gx has to be now also in the domain of f. Moving from here to here is actually like moving from x to f of g of x. We're just going to show the flowchart kind of, and we're really going to check that everything can flow. Here is f of g of x. So we start with x, and we apply g of x, and we get g of x. Then we have to apply f to get f of g of x. So let's see. In order to be able to flow in the first pipe, the blue pipe, because this function is 1 over x, we have to get here that x cannot be 0. But in order to flow here, to get the square root of gx plus 1, gx, which also equals 1 over x, has to be greater or equals to -1. From here, we have to do exactly what we did before, so I will do it quickly. We get an inequality, and as you recall, we have to have 0 on one side of the inequality, and then we are doing analysis on the real line, exactly as we did before. I'm going to do it really quickly. And we get that, which is this, that x is less or equals to -1, or x is greater than 0. And now we observe that it's also true that x is not 0 here, so the domain of h is this.